Hello, in this screencast we're going to take a look at acid-base chemistry a little more, and specifically starting off with some neutralization reactions. Keep in mind a neutralization reaction occurs when mixing a solution of an acid and a base, and that usually will produce a salt and water as its products. We're going to see a couple exceptions, notable exceptions in this screencast. Also important to recognize that acids are solutions that ionize an aqueous solution to make H+ hydrogen cations, and bases are substances that react with those hydrogen ions. It's an easy way to keep acids and bases clear and straight in our heads. And then also don't forget that strong acids and bases are also strong electrolytes, which means they completely ionize in solution. Okay, so if we were to take a look at some of these kind of equations, and for example, if we were to take a base like potassium hydroxide, KOH, and react it with an acid like HCl, hydrochloric acid, that's a strong acid with a strong base. It's going to make HOH, hydrogen hydroxide, which we can write as H2O, and potassium chloride, KCl. Now, since potassium chloride is a soluble salt, I'm going to label that as an SS, and hydrochloric acid is a strong acid, and KOH, potassium hydroxide, is a strong base. Those three substances completely ionize in solution, so that means it's going to make K+ cation, plus the hydroxide anion, plus the hydrogen cation, and the chloride anion, and that's going to produce our water, H2O, and potassium cation, and chloride anion. Our net ionic, anytime it's a strong acid, strong base reaction, is going to be the hydroxide anion, in this case, plus the hydrogen cation to produce our water. And that's always going to be the case for a strong acid, strong base reaction. Now sometimes we can have acid-base reactions that form gases as our products also. So for example, if we were to take a carbonate like calcium carbonate, CaCO3, and add that, which calcium carbonate is normally a solid, and we were to add that to our hydrochloric acid, our HCl, we would get calcium chloride as our salt in this case, and then we'd expect to get H2CO3 from that, the carbonic acid, but it readily decomposes into water and carbon dioxide. So we get a liquid and a gas from this along with our soluble salt. So in this case, since calcium carbonate is a solid, we would leave that formula together. We don't ionize it. We would ionize the hydrochloric acid, H+ plus Cl minus, and that's going to make our soluble salt, calcium cation, plus 2 chloride anions. I suppose maybe I should balance this whole reaction too from the beginning. And then we're also going to get our water and our carbon dioxide. And those are the bubbles you see forming in this beaker right here on the screen. So now for our net ionic, the only spectator we have which appears unchanged in the process is our chloride. So we get calcium carbonate plus the 2 hydrogen cations will produce calcium cation, water, and our carbon dioxide. So we get a gas forming. This is also true of sulfates, which would make sulfur dioxide in some of those situations. Metal sulfites and metal hydrogen sulfites will produce sulfur dioxide in water. Bicarbonates, so like sodium bicarbonate with hydrochloric acid, will also produce the carbon dioxide as a gas. Metal sulfides, however, like calcium sulfide, CaS, would produce hydrogen sulfide gas in water. So there's some notable exceptions to our true neutralization reactions we need to know. One of the things that you'll see over and over is that H2CO3 is a product that carbonic acid readily decomposes into carbon dioxide and water. It's one of those things that we need to know as advanced placement students. Another special situation is what happens when metal oxides are placed in water. Now, when we place active metals into water, that's a single displacement type of reaction that occurs there, and we'll take a look at that specifically when we talk about single displacement. But when we talk about metal oxides, or base anhydrides, which mean without water literally, the answers to those kind of questions are a little bit different. So most metal oxides are in fact bases, meaning they react to form bases when they're added to water. For example, if we were to take calcium oxide and add it to water, metal oxides are normally basic when they react with water. So in this case, we'd make the calcium hydroxide, CaOH2. So again, if we were to take lithium, Li2O, lithium oxide, and add it to water, we would expect to make the lithium hydroxide. Two of them. Now, this lithium hydroxide is a strong base, so the net ionic equation would look like this. Lithium oxide, which is a solid, plus water produces 2 lithium cations and 2 hydroxide anions. And you have to remember that with a net ionic, you ionize strong acids, strong bases, and soluble salts. So it's a slightly different approach. Well, metal oxides will make bases. Non-metal oxides, however, will make the acids. So, for example, if we were to take sulfur dioxide gas and bubble it through water, now the difficult thing becomes determining which acid is produced. In order to be able to do this, we have to look at the oxidation number on the non-metal oxide. So we come back to the reactant side. Oxygen in a compound will be a -2 oxidation number, so that means the sulfur has a +4. We need to come up with a common acid on the product side containing sulfur and oxygen that would have a +4 oxidation number. Our logical choices are sulfuric acid, H2SO4, and sulfurous acid, H2SO3. Well, when we check the oxidation numbers here, oxygen's a -2, and we have 4 of them, so that's a total of -8. Hydrogen's a +1, and we have 2 of them, so the sulfur in sulfuric acid has to be a +6. In the sulfurous acid, we have 3 oxygens, each one at a -2 oxidation number, and the hydrogens at a +1, so the sulfur has to be a +4. There's our product, H2SO3, which is a weak acid, so this equation, as it's written, is our net ionic equation. So anytime we take a non-metal oxide, so carbon dioxide, and bubble it through water, it's going to make an acid. And keep in mind that the oxidation number of the nonmetal doesn't change. So in this case, we'd get carbonic, H2CO3, carbonic acid. So it's nonmetal oxide plus water is an acid, metal oxide and water is a base. Hope this helps. There's another podcast on oxidation numbers, so you can look for that on the same channel that you found this one on, and hopefully that'll help you out. Let me know if you have any additional questions. We'll talk to you soon.